So if there is no question, then we will jump into today's lecture that builds on top of that, in fact, and covering polymorphism. So we have already introduced polymorphism before. Let's go full screen. Can someone remind me really what is polymorphism and what does it really do? So where did we see it before? For example, in yesterday example for point and point 3D, we kind of discussed this in a high level. Does anyone remember what did we do yesterday? Where did polymorphism appear in our coding example? Okay, so if you don't remember or you are not able to make the connection, so put in mind that we said polymorphism is the concept basically that you really have multiple function definitions. So you have the same function signature across the hierarchy of inheritance, but you want to bind or you want to call a certain one based on the object type you are calling, right? Overriding set method. Exactly, Curtis. Thank you. From yesterday, Ching. Yeah, exactly. Thank you. So again, function overriding or method overriding, this is where polymorphism appeared. So if you remember from our working example here, maybe it's good to show it also in practice. In the point 3D, we had a function called set that has exactly the same signature as the set function in the parent class, right? It has the same name, it returns the same type, and it takes exactly the same number of input arguments and types, right? So it's just the same method. And we said inheritance, in fact, has three main things. By default, you inherit all the members that you're allowed to inherit, including public and protected, right? Including member variables and methods or functions. The second one is extension. When you had a new method or function that didn't exist originally in the parent class. And the third kind of application of inheritance, which is overriding here, that is related to polymorphism, which is you are redefining, re-implementing a function that was originally in the parent. So you are not only inheriting it, but you are modifying its functionality, right? And we call this method overriding. So in the set method here, it has two different implementations, right? One in the child and one in the parent. And we said when you go to the main, simply what happens if you call the parent one and the child one from yesterday example, the correct one gets called based on your object type, right? This is basically method overriding. The child is able to override the same method that it inherits from the parent. Good. So to introduce a different functionality. For example, point 3D here, what it added is inside the set, it also added this line to initialize the third coordinate, right? So now we are building on top of this concept by seeing really how it more dynamically interacts with pointers, right? So polymorphism comes into play more when you have pointers to objects, not just really in instances or direct objects of the class. So let's see how. So again, as we reiterate of what we said before, polymorphism really means having many forms. How to apply this here? Well, a same function has many forms in different classes across the inheritance hierarchy, right? And polymorphism occurs when there is a hierarchy of classes, right? So the concept of polymorphism or function overriding does not exist if you don't have inheritance, right? And this is a comparison we'll do later on that we simply touched on before, which is the main difference between overriding and overloading, right? Function overloading. One of the main differences. And again, what does this mean? It means that a member function will cause different behavior. It will execute different pieces of code based on what object it belongs to. So let's have an example, but this example will extend really what we had yesterday with the point class by introducing pointers, right? Similar to what we do before. Simply, I will give you this example. We'll walk through it, introduce the concept, and then we will continue our point example such that you end up with two examples. So my suggestion is after we go through this example together in the slides, and then we go live coding in our point class, try to apply this example when you study on your own to see really how whether you understood the concept that we prototyped on the point class using the shape class or not. But the idea basically here is very similar to what we had yesterday. So this slide is just a reflection more or less on what we had yesterday, except that it's using pointers as we will see right now. So let me bring in my pen here. Okay, so if we look into the shape class, which is like basically hopefully is visible enough to you. Let me see if I can make it a little bit bigger. No. So the idea is in the shape class, I have, well, two member variables, width and height. And then I have a constructor that is called shape that initializes this. But then what our focus is in the area method itself. So in the area method, I have some sort of code prototype. I do it in line here. So the parent class area, and then it just has the area as the width multiplied by the height. Good. And then I instantiate two child classes out of the shape class. One is called rectangle, the other one is called triangle, right? And then in the rectangle class, I simply override the area method by rewriting its implementation, basically, right? So here, instead of saying parent class area, this is a rectangle class area. Again, it's the width multiplied by the height. In the triangle, well, the area is a bit different, right? So I re-implemented the area method, pretty much similar to what we have done for the set, right? Nothing different so far. And then when I go to the main, instead of defining objects or declaring objects directly out of the class, I define a pointer of type shape. That's the first line I have in the main here, right? Defining a shape pointer. And then I create two objects, one for each child, a rectangle and a triangle, and then initialize them by calling the initialization constructor. What I do next is what is interesting. So now I take the shape pointer and I make it point to the rectangle object, right? So simply what did I do now is in the memory, I have two objects, one for rectangle type, this is called rec, and the other one is called tri, which is the triangle object. And then now I have a shape pointer. And with this line, I'm making it pointing to the rec class. Remember, as we said, once you have a class, this works as your user-defined type, right? So you deal with pointers in classes or objects exactly similar to if you have a pointer to an int or anything else, right? And we have seen it before. So this is not a new syntax of code for you. So simply the shape pointer right now is pointing to the type rec. First question is this a valid code? Or maybe I will ask an earlier question. If you define a pointer of type int, something like int x or int btr, can you make it point to something like a string or let's say character? I don't want to use character because character is special int, but let's say double, for example. So I have a double variable. And then I say pointer is pointing to x. Well, this doesn't seem a valid code, right? Because we said before that the type of the pointer should in fact be the type of the variable you are pointing to, right? If you have a double variable, your pointer type should be a double pointer, correct? But now, applying this rule here, why you think, or you might not think this is valid. So the question is this a valid code? If I have a pointer of type shape, can I make it point to an object of type rectangle? And if no, why? And if yes, why? And this is a bonus mark. Stephen, so does it work because it's a shape pointer and rectangle is a child of shape? Exactly, Stephen. Thank you. So the idea is that, well, the statement that we said multiple times before, and I said at the beginning of the lecture, which is an object of type child is also an object of type parent, right? So if you have rec as of type rectangle, also rec is a valid object of type shape, right? So in that case, you can make a pointer that is of type shape point into it. That's correct. So Stefan, as usual, please send your name to the main TA for that bonus mark. Good. So this is a valid code and it works fine. And then later on, I try to call the area method by saying shape and then call area, right? And then I repoint shape to point to triangle and then I make it point to area. So what you expect to happen is that when shape is pointing to the rectangle, it should be calling the rectangle method, right here in this line. And then when you repoint it to the triangle one, it should be really pointing to the triangle method, right? Because this is dynamic binding that we discussed before. But in reality, this is not going to happen. If we try to run this code, what is going to happen is you will get a result of the original parent class. So you will always multiply the width with the height. If you don't believe me, let's try to apply this to our point class quickly and see what do we get, right? So let's shift to the point class, apply the same thing. So here I have my set method, and I go to the main, and instead of defining objects of type child, what I will do is also define a pointer of type parent. I call it pointer. And then now, well, I will make pointer point to my child object. And then I will try to call pointer set, and then send 10 and 20. But just to make sure which set method we are in, so let's try to print something. So here I go to the set, and then maybe at the beginning I will print something like inside point set method. And I will try to do something similar for the point 3D. So where did we implement the point 3D? Here. And this should be inside point 3D. Good, just to differentiate which method we are calling or binding when we really execute that code. And let's see what do we get. So again, what we're expecting is that since pointer is pointing to the child class, or at least what we want to achieve, we should be calling, well, the child one, right? But if I run, is there something wrong? Yeah, maybe because we don't have IO stream included here. Oh, but in fact, I'm calling IO stream already from the point. Interesting.
I think you're just missing another double colon on the STD.
Oh, the STD, that's correct. Thank you. And what about the point 3D one? Who was that? Who added the comment? Yeah, please just send your name as well to the main TA for a bonus mark. So here we have it inside 3D. This should be in the set method, and yeah, that's correct. You should just do that. Good, and let's rerun. Good, so what do we get here? Well, printing from the constructors, you shouldn't really worry too much, but what we are caring about is point 3D. Let me see, what do I have in the point 3D? So inside point 3D set method, yeah, and this is inside point method. All of this is from constructors, as we have seen earlier, so it's not really our focus. But this one, which one did I get? I got the parent one, right? Not the child one. It says inside point set method, which is in fact the one that is being printed from here, right? Why that's the case? Because this is an example of static binding, right? So simply what happens is that the compiler determines, because now we are dealing with pointers and we are different, like repointing a pointer dynamically. The compiler, I didn't give it a hint on really knowing what is the object that I'm going to point you to in the future, right? So simply the compiler, the way it determines it, it will always use the pointer type, not the type of the object that is pointing to. And here, because I define this pointer of type parent, right? In that case, it will always use the point one or the parent one, right? Regardless really of the type of the object that is pointing to. But this is basically static binding or early binding. The compiler knows this statically. If you were to make the pointer of type triangle or rectangle, then yeah, this is what we're going to try, Maya. Thank you. So let's in fact try this. If I make the pointer of point 3D, let's see what do we get, right? So if I run, in that case, you get the point 3D set method, right? So again, it's determined based on the type of the pointer now, statically, right? Good. So what if I want to change this? What if I want to really apply dynamic binding? I want the pointer, while I'm changing the pointer dynamically, the pointer knows really what function to call correctly, right? Or apply real dynamic binding. In that case, we have a very important keyword in C that is called virtual. So I have to define my function to be a virtual function here. Which function are we talking about? Is the set method. This is really what we are what we care about now in our example. So if I go back to our slides, simply the idea to change this is to I'll just wait for till appear. Yeah. So the idea is to use virtual function because we want to use dynamic binding, that the compiler is able to bind the function dynamically based on the type of the content that the pointer is pointing to, not based on the pointer type itself, right? The way to do it in our slide example is to just add the keyword virtual here in front of the function that we want to apply dynamic binding to. So if I defined area to be a virtual function, now this is going to work as expected. Nothing else in the child is going to change, right? So what are virtual functions? Simply, a virtual function in the base class is declared using the reserved word virtual, and it's just giving a hint to the compiler that this function is going to be dynamically binding. So you need to keep some additional information to know what object, basically what is the type of the object that you are going to point to. And it's more relevant when you talk about pointers, right? So basically it's a signal to the compiler that we don't want static linkage or static binding, but rather we want a dynamic linking, or what sometimes people call late binding, because you do it during runtime, not during compile time. Good. The key feature here is you want the selection of the function. This is what we mean by binding. You want the selection of the function to be called based on the kind of the object that the pointer is pointing to. Good. So if I go back to our coding example, I'm just going to add the reserved word virtual inside our in front of our set method here. And then by doing this, so let's here to the implementation. Well, you only do this in the header file. OK. And then you run your code. And even if, remember, in our main code here, even if we still have the point of the pointer of type point or parent, I'm calling the set method. What did I get now? I just get the child one, right? Point 3D set method, right? What did it do? How did it know this? Is because I defined my function in the parent to be virtual here. In that case, the compiler keeps additional information to track the type of the object that the pointer is pointing to. While it's executing this line, it knows that pointer is pointing to a child, or basically a point. Well, now I changed the point 4D. That's interesting. 4D. Yeah, well, I did something convoluted. Basically, I instantiated something of type 4D, but it's inherited the 3D one. So let's really make it simple. So simply, the point child is of type point 3D, and hence, when the pointer points into it, the compiler is tracking this, and hence it will call the correct set method. All of this coming from the hint that the virtual keyword is giving to the compiler that you want late binding. Good. So there are questions on the chat. So we add virtual to the parent method. Yes, only the parent. Nothing will change in the child. Could you still override virtual functions? That's very important. Yes, in fact, virtual functions are their main use is overriding, right? Which is you define, as we'll discuss right now, you want this method to be overridden because it works as an abstract, or it gives you the abstraction that we have been talking about in the concept of OOP, right? Being able to decouple the actual interface from the implementation. Good. So let's see how that's the case. So in fact, what we have done right now is an example of overriding the virtual function, right? In the parent class here, I had one implementation. In the child class here, I had a different implementation, and I was able to override it, right? And call this one. So yes, I mainly overrode it. So now maybe the question that comes out of this is that, am I mandated to really override it? So does point 3D class have to override a virtual method? Well, the general answer is no, right? In fact, you don't have to. You don't have to re-implement, right? If you didn't re-implement one, in that case, you will just really take the parent one as is, right? And we'll discuss this in a bit of a second here in this slide. Good. Is there any question related to the coding example? So we understand the key difference here is now with using a method as virtual, what function to call is really related to the type of the object that the pointer is pointing to, not the pointer type itself. So usually people use this a lot when you really define a pointer of type parent, because again, a pointer of type parent now can point to any child, and you dynamically change this, right? You dynamically change what the pointer is pointing to during runtime, and then you call the correct method accordingly. Good. So as we said, you only define a virtual function inside the parent class or the base class. Child classes don't change. If a base class declares a virtual function, it must implement the function even if the body is empty. What does it mean? So you must have some sort of an implementation to the function, even if the implementation does nothing. It's just an empty bracket. And again, to answer your question, virtual functions, yes, can be overridden by the derived class, as you have seen, but you are not required to do so. If you didn't implement it, then you will use the one from the base class. Good. So that's in fact a very good question, Stephen. So Stephen question, just to mention it to everyone, is in that case, if I know that I want to call the set method in the rectangle class, for example, or in the point3D class, why do I really from the beginning define the pointer to be of parent type and just suffer all this hassle, right? The key answer here is you might not know really statically, based on the dynamic behavior of the program, what child class you're going to call, right? So here, Stephen, you assume that you have all this information statically, that I'm always going to call this method of this child. I will give you one clear example. Again, assume you are writing a library for graphics operations. Like I will take this shape example here. I will extend it by adding a triangle, rectangle, circle, other things like hexagon, etc., etc., etc. And then you want to have an interface. You add a library, and then you want to allow the user to simply call multiples of these shapes, right? And you operate on them. And each shape would have its own area method, for example, in our example here. Now, what object the user is going to create, well, depend on the user use case. You might not know beforehand, right? So you're not writing the main yourself. But you want to write something dynamic enough that you really allow the user, for example, to have a database of objects, of shapes, and each one is of different type, but you still call the correct area. So you want some dynamic operation on your library, right? You don't want to really statically know everything you want to know in compiled time, right? Does this make sense to you? So you basically, this dynamic action is really the added value here, right? If you know everything statically, yeah, sure, you don't need dynamic binding, right? Good, thank you. Great. So now, if you didn't, we said the base class or the parent class would have to implement the virtual method even if it's an empty implementation, right? There is a special type of virtual function that is called the pure virtual function. It's a virtual function that basically doesn't have an implementation inside the parent class, right? And in that case, the way you write this is just define it with the prototype and then you say equals 0. That means I'm not going to implement it. In that case, it's a pure virtual function without an implementation in the parent class. In that case, we call this class an abstract class. Why that's important? Because this is a materialization of the abstraction concept we discussed earlier in the OOB, right? Is that you want to separate. So simply, let me try to add a quickly new slide here. If you remember, we said one of the important concepts of OOB is abstraction, right? So as a developer, you want to separate the interface from the actual implementation details. And then you expose to the user only, here you set your user, you only expose to the user the interface, right? One way to materialize this in reality is to define what we call an abstract class, a class that only has methods, signatures, without implementation. and you leave the implementation detail to the child classes, right? So in that case, if you have, so we call this as an abstract class. And in C++, an abstract class is a class with at least one pure virtual function. Good. One point is that given that it's going to be an abstract, you are leaving the implementation to another child class. You cannot really create objects of this abstract class. So if you try to create an object of shape here, if you made it pure function, pure virtual function, you will get an error basically, because you cannot create a variable or an object of type abstract class, which makes sense because again, it does not have an implementation. It's only an abstraction of the interface. So you want to still implement it. Good. If there is a child class out of this parent class, it must implement all the virtual functions. If it does not implement all the pure virtual functions, then it will also become an abstract class. Good. So let's really see how do we have this in our example here. If I go back to the point class, and now I define it as a pure virtual method. Let's say even I say it takes no input parameters. It wouldn't really matter. So you just leave it as is and then say 0. So in that case, it will not have any implementation. So I will go here and maybe comment this out. Now point itself becomes a pure, becomes an abstract class. So let's really try, if we try to create an object out of point, what we will get, right? I told you that's illegal, but let's really try it to see it in action. So in that case, you get an error here in line 17, tells you that you cannot declare a variable point parent to be an abstract type of point, right? So this is basically what we said is you cannot create objects out of an abstract class. And then you leave the implementation detail to the child. So if I just comment this out and continue, in fact, I end up having everything as we had before, right? In reality, people most of the time do this to, again, separate the concerns, separate the interface that you expose to users in a clean abstract class with only virtual methods that would have the signature of the functions, and then they implement it differently. So that's one way of separation of concerns. The second one is specialization, basically. So you keep one interface, but you might have different child classes that would have different implementation. In our example of the shape class and the graphics, the area, for example, it might not make any sense to really have an area implementation. So if I go here, it might not make any sense, in fact, to define the area to be the width by the height, right? In the shape class here. Because the shape is, in fact, you don't know what shape is this, right? So it's not intended really to have an accurate area. So it's better to leave it as virtual and then leave it to the specific shape. If it's a triangle, you calculate the area in a certain way. If it's a rectangle, well, sorry, here I was referring to the rectangle one, should be this one. And then if it's a rectangle, you implement it in a specific way, which is the width by the height or simply the area of the triangle down there. Good. So here it makes sense, in fact, to remove the implementation of the area from the parent class shape, because again, you don't know what shape it is, right? You might still leave it as a placeholder, right? So there is basically a trade-off. It depends on the use case. Sometimes people leave inside the virtual function some shared kind of code base. For example, some debugging messages, things that are independent of the shape itself. And then you leave the actual shape for implementation when it goes to the child class. So let me stop and see if there are any questions here.